Now we're going to simulate the diode circuits that we have for this lab. So open LTSpice and create a new schematic. And from here we're going to start placing components. So first thing we need is a diode. It's right there. And we also need a resistor. And we can rotate it. And next thing we need is a voltage source. So let's go to component, look for voltage, and place that down. And then we need a ground, which we'll put here. And wire it all together to complete the circuit. Just going to rename some things. And for voltage here, I'm just going to put 0 for now. Resistance, I'm going to set to 0, and I'll explain in a second. And for the diode, if we right click on that and pick new diode, we're going to choose the 1N4148. Click OK. And that will incorporate the SPICE model for you automatically. Last thing I'll do is add some labels. VD for this net, and I'll call this one VS, I guess. Okay, so this is the circuit for the first simulation. I made this 0 ohms because what we're trying to get out of this is the diode current versus diode voltage curve. And in order to easily plot that with LTSpice, it's easiest if you just make this voltage source equal to V diode. If you have some resistance in between, then there's some IR drop across the resistor, and as a result VS is not equal to VD, and the plot won't look quite right. So by making this 0 ohms, there's no IR drop here, so VS is equal to VD. We can't do this in hardware, but just a little trick we can play in order to make this simulation a little nicer. So what we want to do in this sim is to sweep VS. So let's go to simulate, run, and we want to do a DC sweep. My source name is VS here. I'll do a linear sweep from 0 to 0.8 volts at 1 millivolt increments. And I want to plot the diode current. It didn't quite come out right. Oh, I plotted the voltage that way. Here we go. So here's the diode current in green, or in blue. I'm going to change the color here to green because it's probably easier to see. And you can see it looks exponential, especially at the higher voltages. You can see that dip up quite a bit. So what we're looking for from this simulation is, it's actually this one, LTSpice schematic image for IV plot extraction. So you want to get a picture of this schematic. You can use snipping tool or whatever other tool you want to use. I don't have it pinned yet. So we're gonna grab a picture of that. You can just paste it in here. Oops. And diode IV curve we can get from this upper plot. I'm going to make this a little bit bigger here. And it didn't want to resize this for whatever reason. So before I grab a picture, I'm going to just grab a couple data points. So if I click on the signal name up top, that'll bring up the cursor. And should be able to right click and do draw cursor position, and it'll give you the XY coordinates. And I'll just do that a couple of times so we have a couple data points. Okay. And now you can get a picture of that as well. And you can resize the picture if you want, so it fits in the box. Up to you. Okay, looks good. And from this data we can figure out N and IS based on the methods from the previous Prelab part. You can use the 2 data point method. You could use the zero bias to figure out what IS is. So let's have a look and see what that gives us real quick. If I bring the cursor all the way down to 0, let's see what that says. 0 volts, 0 amps. So maybe the precision's just not there in order to get it. So that method might not work in this case. So you could use the 2 data point method, or you can get multiple data points and plot it in Excel and use the best fit exponential function method to figure out N and IS. So once you have those, you can put those here. The next part is to do the half-wave rectifier. So if I go to that circuit in the lab, it's a 1K resistor and 10 microfarad capacitor. Let's go back to our schematic and do, before you move on, you might want to save this stuff. It's up to you. You don't have to. At the end of this, you have to submit some LT-SPICE files, so if you want to separate each part of the lab into separate saves, you can do that, or you can just submit your final LT-SPICE schematic, and that's okay too. Okay, so we have to move some pieces here to construct the half-wave rectifier. I'm going to move that over there. Move the diode, rotate it. Here we go. I need to rotate this. And we need a capacitor. Wire it all together. Change this node to be V out instead of VD. Resistance is 1K, and this was 100. 10 microfarads. Actually, I wasn't supposed to add the cap yet, so I'm going to delete the cap for now. We'll add it back in a minute. So this is the half-wave rectifier circuit, and I'm going to delete this DC operating point thing because we don't need that anymore. I'm going to delete that. And now we're going to do another simulation. So run. This time we want to do a transient simulation. The frequency of the source is going to be 60 Hertz based on what the lab tells us. Somewhere, probably tells us down here. Yeah, 60 Hertz. So that's a period of 16.66 milliseconds. If we want 3 periods, we would do 50 milliseconds. Start saving after time 0, and we'll make the step size kind of small so we can get lots of data points. I don't think we have to check any of these other ones. Just click OK, add the data point. I forgot to set up the voltage source, so it's not going to do anything. So let's change the voltage source to be a sine wave. 0 volts offset, let's see, 10 volts peak to peak means a 5 volt amplitude. So if it's going to swing high 5 volts and low minus 5 volts, so that the peak to peak difference is 10 volts. Frequency is 60 Hertz. No delay. You can just leave the rest of this blank. Okay, and we want to plot VS and Vout. And let's rerun the sim, and there we go. There's our half-wave rectifier circuit. So let's add some data points here, because we're going to need some for our calculations. So I'll click on the green curve, and we'll pick off a couple points. So right click, draw, add cursor, switch to the other one, right click, cursor. You want to get 2 data points corresponding to the same time, but to the 2 different curves. And you'll see why when you do the VD-RD calculation. That they give you the equation for in the lab. And let's add another one over here somewhere so it's easier to see. So right click, draw, cursor, position, right click, draw, cursor position. And I just move this guy out of the way. There we go. So let's get a picture of this. So you need a picture of the schematic, copy, paste that in here, and you need a picture of the waveform. So let's do try to make it nice. Paste that in here. You can resize it later. And from this we need to get a few different things. Peak offset is, let's just minimize that. Peak offset is going to be the difference between the peak values. So pretty self-explanatory. If you go to roughly the peak and add a couple data points, draw cursor position, you can take the difference in the voltage values and that will give you the peak offset, which looks to be around 660 millivolts. So you can take that there. Conduction time is how long does the green curve conduct? How long is the output greater than 0 volts? And you have to approximate this a little bit, and you can zoom in to get more precise values, but looks like it starts conducting around there and it stops conducting somewhere around here. It doesn't have to be super perfect, just the concept is good enough. So the conduction time is you take the difference between those two time points, 24.78 and 16.86. That'll tell you how long the output is conducting. So that looks to be about 7 milliseconds, 7 point something milliseconds. Conduction ratio is the conduction time divided by the period of the input, which is 16.667 milliseconds. So this value should be slightly less than 0.5. If it was exactly 0.5, then these green and blue curves would overlap for half the period, but you can see that the green conducts for less than half of the time that the blue curve is above 0. So it's got to be, the ratio's got to be less than half, probably around 0.48 or so. RD and VDO we can get with two data points that I had mentioned before. If we go back to the lab document, there's an equation they give you here where VO is RL over RL plus RD, VS minus VDO. And in this equation, the unknowns are RD, little rd, and VDO. But if we have two data points corresponding to the input and the output at the same time, we can plug those into this equation and create two separate equations where RD and VDO are the unknowns. So RL is 1K, VO and VS correspond to these voltages here. So VO is VO is 1.58 volts when VS is 2.185. So put that in one equation. In the second equation, you would use the second set of points. VO is 3.153, where VS is 3.792. And you can solve those for RD and VDO. And ideally, RD is very small, and VDO is probably somewhere around 0.7 volts, similar to the peak offset. And once you have those calculated, you put that here, and that will complete this section. The last thing we have to do is add that capacitor, which I accidentally added earlier. So wire that up. This is 10 microfarads. C load. And you just rerun the same sim. So click the run button, and this time the output doesn't quite settle to 0 because the capacitor is slowly discharging the out. So in this scenario, I'll get rid of all these markers I put on here. I'll just restart. I'll just rerun the sim, get a fresh look. VSVO. For this, we want to look at what the ripple is. And the ripple is the peak to peak of the output waveform once things settle, which is not the first few milliseconds here, but it's probably the second and third period is okay to look at. So let's click there, and let's get a couple data points. Right click, cursor position, and That looks about the min. Cursor position. I was trying to delete these things, but I guess I can't maybe. No, I can't even move them. Here, just trying to move them out of the way for our picture. Okay, can't move that one at all. Anyway, so we have the max and we have the min. If we take the difference, that will give us our ripple. So we want to grab schematic image. Oh, let's retry. LT Spice open. Schematic image. Copy that. Paste that here. And our waveform with our measurements labeled. Okay, I accidentally closed out of it somehow. I think I just zoomed in on accident. So copy that, put that here. And you can calculate the ripple from the difference in the max and the min of the output waveform. And that's it. So once you've done that, you've gotten all your pictures, you can include this in the Prelab submission Dropbox along with your LT Spice files. Don't forget those. And that's it for the Prelab.